Let's take a look. All right, so 15.15, let's start with the compound here. We start with these methyl protons here. I'll just ask my students, are these protons split by any protons, or would we just get a singlet for these ones? One's in the red box. Splitting, yes, no? Anybody have an idea? Yeah, thanks, Clinton. Absolutely. I'm going to get a singlet for these ones because they're not split by any protons. Singlet. You go, just draw one of those protons. If you go 1, 2, 3, or 3 bonds away, there's no proton attached. So, yep, those ones aren't split by anything. The same thing applies to this methylene here. Those protons are also going to give us a singlet. So we'll write that down, singlet, because they're not split by anything. Does anybody recognize this alkyl group here that I have in the yellow circle? What type of alkyl group that is? It's one of the alkyl groups we've looked at today. It's also one that we covered in chapter 4. Yeah, absolutely. Absolutely. Yeah, I agree with you, Nicole. It's an isopropyl group, isn't it? And we saw that there's some characteristic splitting of isopropyl groups. We have all 6, let me get a green pen here. We have all 6 of these methyl protons. Let's put there's 6 of those, and they're only split by this one proton here, right? There's only one proton in this methine, and so these are going to give us a doublet for all 6 of those. And then the one that I have in the red box, the other one, it's split by all 6 of those. So 6 plus 1 gives us 7. And so we would see a septet for that proton. Any questions about that one? Give me a thumbs up if you follow me then. Is everybody with me on the splitting for those protons? All right, great, great. Okay, well, let's take a look at the next one. We'll just scooch over here a little bit. This one, hopefully you noticed when you took a look at this one that it's got an axis of symmetry down here, or a plane of symmetry if you rotate this 180 degrees. And therefore, you can clearly see that these protons and these ones are chemically equivalent. These protons and these protons are chemically equivalent. Then I have a methine here, and then I have a methyl group down here. So if we start with the red protons, here, could anybody tell me how these would be split? Would I get a singlet, doublet, triplet, quartet, pentet? Anybody? For the ones in the red box, they're coupled next to the 2 protons in the blue box only. You think about 2 plus 1. What should we see? We should see a triplet, right? Because they're split by these 2 protons. Okay, so 2 plus 1 gives us 3, and so we should get a triplet for these, and we should also get a triplet for these protons as well. All right, what about the protons in blue? Could anybody tell me how they would be split? They're going to be split by 1, 2, 3 protons. And what happens when you have 3 neighboring protons? What are we going to see here? A singlet, doublet, triplet? We're going to see a quartet. Exactly. So we see a quartet. Perfect. So we're going to see a quartet for both of those. Then we have the green one, the methine. Could anybody tell me about that methine proton, the green one? What kind of splitting would I see there? It's coupled next to the 3 protons of the methyl in the black box. So 3 plus 1 gives us 4. And so that methine is also a quartet. So we have a quartet. And the last one is going to be the 3 protons in the black box. those are only split by this proton. So 1 plus 1 gives us 2. And so these ones are going to give us a doublet. And that, my friends, is how you determine multiplicity using the n plus 1 rule. That's what this is. It's nothing more than an application of the n plus 1 rule. And it's a rule that you really want to make sure that you're fully aware of and that you're able to apply it moving forward. Well, let's take a look at some spectra and some multiplicity as it applies to spectra. Question 15.17 asks us, below are some NMR spectra. Identify whether these compounds are likely to contain an ethyl, an isopropyl, or a tert-butyl group. If we look at A, you can see we kind of have like a multiplet down here above 7. So this one looks like a multiplet to me. Multiplet. This one here, you can see that you've got a total of 1, 2, 3, 4, 5, 6, 7 peaks. So this is a septet, and this integrates for 1 proton. And then over here we have a doublet that integrates for 6 protons. Can anybody tell me in A, do you see either an ethyl or an isopropyl or a tert-butyl group in this spectrum? There's one of these in here. Could anybody tell me which one is present here? Yeah, absolutely. Thanks, Kiana. Yeah, it's the isopropyl, isn't it? We have the isopropyl right here. We have an isopropyl. How do we know that? Because if you draw an isopropyl, you have a methine coupled next to the 7 protons of these 2 methyl groups. Again, these are the 6 protons that give you a doublet. And then this methine proton is split by all 6 protons. So that integrates for 1, but it gives you a septet. Okay, what about, let's see, in B, let's investigate here. So the first one, the signal with the highest chemical shift, 1, 2, 3, 4, 5, 6, 7. So we have a septet that integrates for 1 proton here. Move that over a little bit. Then if we scroll down here, we have a quartet. This is a quartet that integrates for 2 protons. Then these are kind of close together, aren't they? Well, hopefully you can see that, you know, if you draw a line here, you can see that this is a doublet that integrates for 6 protons. And then this one down here is a triplet. This is a triplet that integrates for 3 protons. So I actually see 2 alkyl groups in here. Could anybody identify any alkyl groups in here? An ethyl, an isopropyl, or a tert-butyl? Well, I'd say that there's 2. Okay, I'd say we have an ethyl group. If you look at the quartet that integrates for 2, and then we have a triplet that integrates for 3, that would be an ethyl group. And then if we look at the doublet that integrates for 6, and then the septet that integrates for 1, that would be an isopropyl group. And so we have an ethyl and an isopropyl group in our molecule in 15.17b. All right. Is everybody with me on that? Give me a thumbs up if you follow me on alkyl groups. Oh, I see somebody typed the right answer in the chat. I might have missed it, Kiana. Thank you very much. Great. Yeah, pretty cool. And what you're going to find is that, you know, once you get these things down pat, they never change, right? If you take organic chemistry 2, 10 years from now, the ethyl group, the isopropyl group, the tert-butyl group, they're not going away. And the splitting pattern will always be identical. Again, let me encourage you to do all the practice problems. If you do them, it not only gives you some knowledge, but it just solidifies everything that you already know. You put it into practice and you're not going to forget it. You're going to be able to recall it on any quiz or exam. Well, let's take a look at section 15.8. Now, chapter 15.8, you see that I say skip here, but if you go into the suggested practice problems on Canvas, oftentimes, like if you go into Canvas and you scroll down to chapter 15, so where's chapter 15 here? And you look at the chapter 15 suggested practice problems. Let's open it up. If you look in here, there might be some problems that I recommend that you do that come from or are based off of section 15.8. Now, if you're thinking like, why would you ask me to do a problem that, or ask me to work on a problem that you're not going to ask on a quiz? Well, the rationale is this. It's great practice to try to draw a proton NMR spectrum, but it's difficult to get students to do it over a computer. And even when I do paper exams, it's very difficult to do because it's very difficult to grade. Okay, sometimes students will draw, their drawing skills are really on point and the quartet looks perfect. Other times, it's very difficult to tell what a student's trying to relate to me. So I wouldn't say skip this skip this section as in don't read it and don't care about it. I would just tell you, read it on your own time. Take a look at a couple of the practice problems. I won't ask the exact problems from that section, but it's worthwhile knowledge to have. All right, so that covers that. Now, one of the most powerful demonstrations of NMR is being able to use it to distinguish between compounds and to be able to do it so quickly, just with extreme speed. And if you're wondering, well, hey, Mr. Dion, I thought you always said you weren't a speed guy and you're not into working fast. Well, not necessarily, but what I'm saying is if you're trying to run a business, if let's say you're a chemist in the pharmaceutical industry and time is money, well, NMR can oftentimes just find ways or you can use it to identify compounds very quickly. Let me show you a really cool scenario. Check out these three molecules. These are called xylenes. The first one is orthoxylene, and the one in the middle is called metaxylene, and the one on the far right is called paraxylene. The names aren't important, but if you were to try to distinguish between these molecules using infrared spectroscopy or mass spectrometry, I mean, really, how would you do it? You wouldn't be able to because they all have the same functional group, they all have an aromatic ring, and they all have the exact same mass. They're all aromatic, so the fragmentation is going to be very similar. You cannot use IR and MS to distinguish between these two. I mean, there might be ways to do it, but it would be very difficult. Whereas if you ran a proton NMR in 1 second or like under 5 seconds, you could look at the proton NMR spectrum and say, which compound it is. Now, why is that? Because the one on the far left produces 3 signals. The one in the middle produces 4, and the one on the far right produces 2 signals. So just by looking at the number of signals, not even determining, is this a singlet, is this a multiplet, whatever, that doesn't even matter. You just look at the number of signals. How many signals do I have? And you could distinguish between these 3 compounds very fast. Let's take a look at a question. This is 15.21. How would you use proton NMR to distinguish between the following compounds? Let's imagine you're working in a lab and somebody gives you 2 jars and they have 2 clear colorless liquids in them. And one of them is this compound, the other one's this compound, but you don't know which is which, right? Let's say the labels fell off or something. How would you distinguish between these two? You could run a proton NMR on both of these and you could distinguish between them in seconds. My first question to you guys, to my students is, could anybody tell me how many signals would you get in the NMR spectrum of this compound? How many total signals would you get? Keep in mind that there is a plane of symmetry here. It's not a very good plane. There's a plane of symmetry running through the molecule here. How many total signals would I see here? Could anybody answer that? This would go back to section 15.4, determining the number of unique protons. Okay, in this one, there would be a total of 3 signals. Okay, 3 signals. So what would they be? Well, this methylene and this methylene are chemically equivalent based on the plane of symmetry. We have these 2 protons being chemically equivalent for the same reason, the plane of symmetry. And finally, these 2 protons are chemically equivalent based on the plane of symmetry. And so for this molecule, you would see 3 signals. However, in the molecule on the right, there's no plane of symmetry. No plane of symmetry. And if there's no plane of symmetry here, that means that these 2 protons are going to give you a unique signal. These ones will. This one will. This one will. This one will. And this one will. So we have a total of 1, 2, 3, 4, 5, 6 signals that we would get for this molecule. 6 signals. And so very quickly you can tell the difference between 3 signals and 2 signals, and you would be able to determine the difference between these compounds. You would say, well, the one that's 3 signals, that's this compound, and the one with 6 signals is this compound. Okay, let's take a look at B. B is a little more interesting because these 2 compounds both have something in common. They both possess a tert-butyl group. You see a tert-butyl group here and a tert-butyl group here. And they both possess a methyl group. Now, the methyl groups, neither of them are coupled to any protons. So this would give you a singlet. This would give you a singlet. And a tert-butyl group is always a singlet. So this is a singlet. And this is a singlet. They both give you 2 singlets. How could anybody tell me what you would have to use to distinguish between these 2 compounds? We can't use multiplicity, and we can't use the number of signals. They both have 2 signals. Could anybody tell me how you would distinguish between these 2 compounds? What else could we use? Exactly. Thanks, Clinton. You're 100% correct. We would use the chemical shift. Tracy, you're both on the exact same thing, and you're both right. It's going to be the chemical shift, isn't it? Let's take a look. Let's just look at the singlets that come from the methyl groups. Okay? Maybe I'll circle this one and change it to black. Okay, so I'm going to change this one to I'll change this one to black. Okay, and we're going to talk about those 2. So the one in blue, let me just zoom out here a little bit. The one in blue, I get a singlet that integrates for 3 protons. But what's the chemical shift? The baseline of a singlet, the baseline of a methyl was 0.9 parts per million, but it's alpha to a carbonyl. So that means we add 1, and we get a chemical shift of 1.9 parts per million for this proton. So this is at 1.9 parts per million. Whereas this one here, let me use my black pen, this one also gives you a singlet that integrates for 3 protons, but now what's my chemical shift? I have the baseline of 3 parts per million, but it's alpha to the oxygen, the sp3 hybridized oxygen of an ester. So for that, we add 3. Huge difference between the 2. This is going to have a chemical shift of 3.9 parts per million. And so very quickly, if you look for the singlets that integrate for 3, the one that's at 3.9 parts per million, that's going to be this compound. And the one that is at around 2 parts per million is going to be the compound on the left. Give me a thumbs up if you just follow me on the rationale. Even if you're saying, you know what, Mr. Gann, I think I need to study this for a little bit. I'll figure it out. But awesome. Even if you just follow me on the rationale, you're sitting pretty. Could anybody suggest an idea for C? I'm sure somebody's been looking ahead. Could anybody tell me how you might distinguish between the 2 compounds in C? Even if you're not sure of the correct terminology, you can just put it into whatever terms you want, and I'll try to figure out. Exactly. So what Nicole is saying and what Tracy is saying, they're both saying number of signals. They're both 100% correct. Because if we look at these 2 compounds, you can see on the one on the left, it's going to produce 1, 2 signals. All the protons, all 4 of them in the blue oval, are chemically equivalent. All four in the red oval are chemically equivalent. So two signals. Let's scribble that down. Two signals. Could anybody just throw it out to me? I didn't. Yeah. How many signals would I get for this one? I'm going to test you guys. And if you guess wrong, it's not a big deal. I don't care. This is a safe space. Yes, absolutely. It's three, isn't it? You get three signals. Why? Because you have these four protons are chemically equivalent. These four protons are chemically equivalent, but then you get this guy down here that's unique. So we get three signals. Perfect. Again, very quick. We could just look at the NMR spectrum. Two signals. This compound. Three signals. Going to be this compound. Just like that. Boom. We were able to determine the difference between the two. I'm just going to go. I'm not going to stop recording right now. I'm just going to go grab a quick drink of water. I'm going to let you guys sit on this one just for a second. See if you can determine how you would differentiate between the two compounds in D. I'll give you a second. All right. Could anybody tell me, I mean, you're not going to use splitting in D. You're not, so you're not going to use multiplicity. You're not going to use chemical shift because really you have the alcohol and then you have aromatic protons. You're going to use the number of signals again. My question to you guys, I just like finding out what my students know. What if I put this compound in a yellow circle? How many signals would I see for this compound? Could anybody tell me how many you'd see for this one? The one in the yellow oval? Okay. Is there a plane of symmetry in the molecule? The answer is yes, isn't it? There is a plane of symmetry in this molecule. There's a plane of symmetry going down here. That's not very clear. There's a plane of symmetry going down like this. And so that means that these protons are chemically equivalent. So that's one signal. These protons are chemically equivalent. That's a second signal. And then this proton is unique. So for this compound, we're going to see a total of three signals. Whereas for this compound, there's no plane of symmetry whatsoever. This proton is unique. This proton is unique. This is unique. This is unique. And this is unique. Where's my green pen? There we go. So for this one, we have a total of 1, 2, 3, 4, 5 signals. 5 signals. So compound on the left, 5 signals. Compound on the right, 3 signals. And that's how we would differentiate between the two. If you go into the chapter 15 module on Canvas, you'll see that I have a little document posted there that I made a while ago. It's called A Strategy for Solving Spectra Problems. And it gives you all, just a few tips on, how to solve, any problem that deals with spectra, meaning if you have NMR, mass spec, IR. But what I do if I have an NMR spectrum, is try to follow this order of operations here. First thing I do is if I'm given a molecular formula, I'll always calculate the HDI just kind of quickly to see, do I have a double bond? Could I have a ring? Those kinds of things. If you have an HDI of 4 or greater, oftentimes it means you have an aromatic ring. Not always, but a lot of times. So I might look for things like that. The next thing I would do after the first step is done is I would just look at the number of signals. Do I have 2? Do I have 3? Could there be symmetry in the molecule? Because oftentimes if you have a lot of protons but only a few signals, it means you're going to have some kind of plane of symmetry somewhere in the molecule. Next, I look at the fragments. I say, is there an ethyl? Is there an isopropyl? Is there a tert-butyl? That kind of thing. And then once I've got that done, I try to put them in a structure. And then once I have some kind of structure, I ask myself, first, I kind of go in between here and say, does this structure even make sense? And then if it does, if I think it makes sense, you can go back and you can kind of use, what was it, table 15.1, and you can kind of estimate the chemical shifts and just to ask yourself, do these numbers work? Do they line up? Like, do they actually concur with what I know? And if they do, then you're probably good to go, and that's sort of the strategy that I like to take when I'm solving an NMR problem.